very important test, and it is used in many theorems and examples for the uniform convergence. Let summation n going from 1 to infinity on un be an infinite series of functions defined on subset E of a metric space, and let Mn be a sequence of positive real numbers such that the infinite sum on Mn is convergent. And if mod of unx is less than equal to Mn for all n greater than equal to capital N for all x belonging to E, then this infinite series is uniformly convergent on E. Before starting with the proof, let's recall these definitions and theorems first, because I'm going to use these results in the proof. So first one is, a series of functions summation n going from 1 to infinity on Fn is said to converge uniformly on E if the sequence Sn converges uniformly on E, where this Sn sequence is F1 plus F2 plus F3 up to Fn. Second, Cauchy's criteria for uniform convergence, that states the sequence of functions Fn defined on E converges uniformly on E if and only if for every epsilon positive there exists a positive integer n depending on epsilon only, such that for all x belonging to E, the mod of Fnx minus Fmx is strictly less than epsilon for Mn greater than equal to n. Then third one is the Cauchy's general principle of convergence. We have proved all these results in the previous contents. So this states that the series summation n going from 1 to infinity un converges uniformly on E if and only if, given epsilon positive, there exists a positive integer n such that the mod of summation on urx, where r is going from n plus 1 to m, is strictly less than epsilon for all n greater than equal to n for all x belonging to E, where m is strictly greater than n. Right? Now what is given to us? An infinite series, the summation on un, right? And it is defined on the subset E of a metric space. And secondly, it is given that Mn is a sequence of positive real numbers such that the infinite sum on Mn is convergent, right? And if mod of unx is less than equal to Mn for all x belonging to E and for all n greater than equal to n, then we have to prove that the infinite series un is uniformly convergent on E, right? Okay. Now since the summation on Mn, since the infinite sum on Mn is convergent, this is given to us, right? Because this Mn is free from x, right? So if the sum is convergent, the infinite sum is convergent, then it is also uniformly convergent. Because for the uniform convergence, the positive integer n depends only on epsilon. It is independent of x, right? So this infinite series is uniformly convergent also. So therefore, it is uniformly convergent. Right? So now I'm going to use the Cauchy's general principle, the third one, that states the series, infinite series on un converges uniformly on E. This is what the point is there. If and only if, now applying this definition, if and only if given epsilon positive there exists a positive integer n such that the mod of summation r going from n plus 1 to m urx is strictly less than epsilon for all n greater than equal to n for all x belonging to E, where m is strictly greater than n. I'm going to use this result now. Now as this infinite series is uniformly convergent, so by Cauchy's general principle of convergence, for every epsilon positive, there exists a positive integer n such that the mod of mr, where the summation starts from r equal to n plus 1 up to m, this is strictly less than epsilon, right? For m greater than n and greater than equal to n, capital N, right? Okay, let's define Snx to be equal to u1x plus u2x plus u3x up to so on, up to here it is n, so it is u and x, right? Then for m strictly greater than n, what we have done in the proofs of the previous results, you must remember that the mod of smx minus snx, this is equal to, yes, the summation r starting from n plus 1 to m urx, isn't it? This snx is starting from u1x plus u2x up to unx, and smx, this series is u1x plus u2x up to unx, but also adding the terms because m is greater than n, strictly greater than n, so also continuing further un plus 1x plus un plus 2x up to so on, it is m here, so up to umx, right? When you subtract these two, this will cancel out, yes, and remaining terms are un plus 1x up to umx, right? So I can write this sum of the series as, I can take in the summation form as urx, where r is starting from n plus 1 and reaching m, right? This is what I have written over here. So this can be further less than equal to summation r starting from n plus 1 to m mod of urx, fine, and that is again strictly less than the summation r starting from n plus 1 up to m. What is mod of urx? It is strictly less than equal to mr. It is given to us that if mod of unx is less than equal to mn, right? So there we are having urx. So this mod of urx is less than equal to mr. As here it is given that mod of unx is less than equal to mn. There we are having mod of urx. So this can be written as it is less than equal to mr, right? So this is given. Further, this is less than equal to, can I write this as mod of summation r equal to n plus 1 to m mr? I can write this in mod, and this is further strictly less than epsilon. So this is strictly less than epsilon for m strictly greater than n greater than equal to capital N. So this is strictly less than epsilon for m strictly greater than n greater than equal to capital N, right? So this implies what we got, that mod of smx minus snx is strictly less than epsilon for m greater than n greater than equal to n. And by Cauchy's criterion for uniform convergence, what this states? Yes, the second result, Cauchy's criterion for uniform convergence. This states that the sequence of functions defined on E converges uniformly on E if and only if, for every epsilon positive, there exists a positive integer m depending on epsilon only, such that for all x belonging to E, the mod of fnx minus fmx is strictly less than epsilon for m n greater than equal to n. This is two-way result. We have got this, right? So from here I can write that the sequence of functions defined on E converges uniformly on E. Here the sequence are in fnx, but we are having here smx and snx. But here epsilon is arbitrary, right? But epsilon is arbitrary. So by Cauchy's criterion for uniform convergence, we write, therefore, Sn converges uniformly on E, right? And now the definition for the first result. What is Sn? Sn is u1 plus u2 plus u3 up to un. If this sum is converging uniformly on E, then using the first result, a series of function infinite series is said to converge uniformly on E. This we need to prove. If the sequence Sn converges uniformly on E, the sequence Sn, f1 plus f2 up to fn, if this converges uniformly on E, we say that the infinite series of Fn is set to converge uniformly on E. So here we are having Sn to be as u1 plus u2 up to un. And this is converging uniformly on E. So from the first definition, we write that then the infinite series un, n starts from 1 to infinity, this converges uniformly on E. Right? Hence the result has been proved. Thank you. God bless.